Okay, thank you everybody for being here. So the first topic today, something I'm presenting on, is around zstd in the browser, or zstd as some of y'all would say. So zstd is a compression algorithm. It's kind of a recent one that has been prioritized by the Facebook team. Today, I kind of want to go over some use cases of it, a little bit of background, a proposal or kind of a request potentially for browser vendors to consider adding it as one of the compression schemes, accept encodings and content encodings that they would utilize in the browser. And just kind of go over some of the ins and outs and why I think it might be a unique fit for the web, for the browser. So I will preface this by saying I am not an expert in zstd. I've used it, I understand it a little bit. We've experimented with it, and I'll go a little bit into that for Akamai's use cases. There's probably other people on this call that are even more familiar, and we could rely on them if we have any more detailed questions. Um, so that's one thing. The other thing is I realize that compression schemes themselves are not necessarily in scope for the WebPerf working group's deliverables necessarily. However, there's a lot of people here that I think are passionate about performance, and this is a decent forum to make a pitch like this. Also, we do have the compression streams API that this working group has looked at in the past, and that API could potentially use zstd as one of the content encodings in addition to gzip that is today. So with that being said, let's jump into it a little bit. So again, zstd is published by Facebook. They have a homepage as well as the RFC 8878. The kind of marketing pitch for it is that it is a fast compression algorithm while still maintaining high compression ratios. I think of it kind of as a more modern replacement to gzip or zlib, deflate, and kind of sits alongside Brotli in many cases, possibly has some additional benefits in some scenarios over Brotli, but it is a modern high-speed, high compression ratio compression algorithm. There's a lot of, so it was released I think a couple of years ago, maybe 3 or 4 years ago. It's been adopted around the web in various tooling, databases, in-place storage, services, etc. There's not much web server support for it yet. I believe there is a Nginx module to compress content with zstd. I'm not sure if it's in any others. I don't believe any of the other CDNs support it. I may be wrong on that. But there are a lot of custom application client server interfaces that are using it. Facebook, I believe, does that. And it is not in any browser to my knowledge today. We at Akamai have been experimenting with zstd for internally. We are using it for at-rest log storage, where it's provided some benefits, significant benefits over gzipping logs. Notably, it's faster and provides smaller files, which is, I think, a win-win for our use cases. So we have started experimenting with it internally, and we are looking into other potential uses for it, and we think that the browser use case might be a good fit. So to kind of share the benefits of it, or kind of where it fits in the world of other compression algorithms out there, the zstd repo publishes this research that they did. I'm not entirely sure of the corpus that they're using here, of the documents that they're using, but this is one benchmark, if you will, that they have published. So the way that you may read this chart is, and I think you can see my mouse. I'm hoping it's not too big, but it's there at least. This dark green line is zlib. So on the x-axis, you have speed. So you want to be further left to be faster. And on the y-axis, you have compression ratio. So higher up is better compression. So ideally, you want to live in the upper left quadrant. If you look at zlib's compression rate over its various levels of 1 through 9, where 1 is fast but not very good compression, and 9 is the highest compression you get, you can kind of see the curve that it offers as far as speeds versus compression. As you get higher compression ratios, obviously the speed in megabytes per second drops. I think zlib's default is around 6. This is around the 6th level. And beyond there, you don't get much higher compression ratio, but you lose speed. The other two algorithms that I would point out that are relevant for this discussion are Brotli, which is kind of the salmon line right here, and zstd, which is this blue line up here. And I think one way that you could read this chart would be if you, for example, wanted to hold the compression ratio equivalent amongst these, amongst zlib, Brotli, and zstd, you could compare their speeds. So zlib lives here at, I don't know, 80 megabytes per second or so, but for an equivalent compression ratio with the others, so you're getting the similar sizes, you often get faster speeds with Brotli and even faster speeds with zstd. And as you move up in compression ratio sizes, if you hold that similar for all three, so this is about the default for zlib, you can still see a higher speed in compressing data with Brotli and zstd. Again, this is their benchmark, so there may be other benchmarks that show different numbers, but I think this is a good starting point. The other way that you could look at this is if you wanted to hold speed the same. So if you wanted to have a consistent amount of time that you're compressing something, you could compare the different compression ratios at that speed. So again, with zlib around the standard of 6, if you're comparing the compression ratio versus Brotli and zstd, they're much higher. I don't know in real percentage points what that is, but say 10, 20, 30% is often what we're seeing with our experimentation. Again, this is one corpus that we're looking at, and there's a lot of different types of data that you can compress on the web, but this kind of gives you just a high overall view of what the different compression algorithms may give you. And I think the interesting thing in this graph to me is kind of the difference in output for Brotli versus zstd. So that's between the salmon and blue lines here. Now, at the higher levels of compression, so when you go to Brotli 11, for example, that's this knot up here, and zstd, again, also you have higher levels of compression. They kind of start, performing kind of similar. They're around the same line, around the same curve. But on the lower levels of compression, so these are, let's say, Brotli 4 or 6, which I think are common for dynamic content, and some of the lower zlib levels, for an equivalent compression ratio, you get better speed with zstd, or for an equivalent speed, you get better compression ratio often with zstd. So again, I think this is kind of like the interesting zone of how zstd in this corpus reacts. The other thing that they publish is decompression speed, and again, this totally depends on the content and compression levels you're using, but zstd is no slouch in decompression. It scales, I think, fairly linearly. I think it does scale based on the compression level, on the amount of memory required, but the actual speed is, not any worse than Brotli and zlib. So that being said, one of the, I think, one would maybe consider trying to get zstd in the browser as one of the tag-along compression schemes besides gzip and Brotli. Obviously, Brotli has had a really big uptake in use over the last few years. I think most major software server clients and CDNs and everything support Brotli. A big use case for it today is encoding static content, where if you are either pre-compressing your, say, CSS and JavaScript files, stuff that's not going to change, at the highest levels of Brotli 11, you can get really good byte savings over gzip. And a lot of people are doing that. They're pre-compressing it as part of their build process, or they're offline compressing it at the CDN. But these high levels of compression are very CPU intensive and are not often suitable for doing it on the fly, like doing it when requested every time. So both Brotli and zstd, looking back at that chart, are very similar in characteristics for compression at the very highest levels when you're spending the most CPU. So I don't think those types of content are necessarily the best utilization of zstd on the web, if it's going to give you just something similar to Brotli. Where I think it really shines, or the use case would be really powerful, is with dynamic content. So I'm talking about non-cacheable content generally, say HTML pages, like your root HTML page or dynamic web app that's spitting out dynamic content from your server, API calls that are spitting out JSON, etc. Where you would traditionally not be spending, like you wouldn't be broadly leavening this data, because you don't want to pay that upfront high CPU cost if you're constantly changing the data and you can't cache it at the edge. Whereas with zstd, what you could choose to do is use one of the lower Brotli or zstd compression levels for your dynamic content. And you would, in this case, zstd would often probably give you a lower CPU cost, because again, in many cases, depending on the content, you can often get higher speeds for an equivalent compression ratio. And that often would result in a quicker time to first byte. I don't know. I can't quantify that for you right now. I think there's some interesting research that could be done here, but it's certainly less CPU I think is good in many cases. Less CPU also translates into less infrastructure costs, whether that's at the origin or at the edge. And it's also been shown, from benchmarking, that zstd is very fast decompression in the client. I think that I will talk about the downsides of zstd and some of the reasons why it's faster in a bit, but it does require a bit more memory usage than gzip, for example, to decompress. But hopefully, some of the lower end CPU devices out there would benefit from spending less time decompressing content. So that's one of the use cases I think would be interesting to explore, which is mostly for dynamic content on the web. The other thing would be in userland space. So we have this compression streams API. It allows you to compress any blob in JavaScript, today just with gzip. It's usable for a lot of different things. I'm not sure exactly how much it is used, but I think the interesting thing that zstd could provide, if it were part of the compression streams API, would be providing a much faster way of compressing for the same ratio in userland in JavaScript, or even more compression ratio than you get out of gzip. And that's kind of this green zone here, the difference between zstd's compression levels and speeds versus zlibs. You can use compression streams for a lot of different things. Obviously, just you can compress and persist and read data out of indexed DB, your binary blobs. Maybe that's important for some aspects for an app to compress data before it stores it within the browser. I think it's interesting for RUM providers and other people that upload data. For us, with the Akamai Impulse RUM, we have our beacon, the data that, all the performance data that we upload. Most of our beacons have resource timing data in it, and that is quite a lot of data. Our beacons can grow from 10 to 50 kilobytes in size, depending on the amount of resource timing data. And that's after we do a lot of string level optimizations around compressing the resource timing tree and stuff like that. It would be useful, and we've looked into potentially using the compression streams API to pre-compress our beacon data with gzip, or something in the browser before we send it out, and just have our server read the gzipped upload. But part of the concern, part of the hesitation in that is using gzip is still costly from a CPU time point of view. And that's where I think we would love to potentially explore zstd as another way of pre-compressing our data before we upload it, especially if we can do it for very fast, for minimal noticeable CPU time cost. And similarly, I think for any other large content that is uploaded to a server, it could be worthwhile to spend some time on the client CPU before it's being uploaded and to save bandwidth. The third thing, another big thing that you may persist and send somewhere is the JavaScript self-profiling data. If you just look at the raw JSON stringified, content of your profile, it's just a ginormous string content, and it could benefit from being pre-compressed or userland compressed with something like zstd. So those are the two main use cases. Certainly, it's not all sunshine and rainbows with any new compression algorithm. There's obviously some trade-offs that you have. From the research that I've read, it's not zstd is not as good at compression on small files, and some of that maybe Brotli does ship on the web today with a shared dictionary. Then I can go over shared dictionaries in a moment. So we would probably need to have some sort of similar shared dictionary for zstd. Once you get a larger file, the file's content itself kind of helps build up its own compression. But if you're working with a lot of small independent files, they may benefit from sort of shared dictionaries to start out with. Another downside is anytime we're talking about adding browser support, we're talking about adding binary size increase from the library, right? So that is a non-zero cost. I'm not entirely sure what the scope of that would be compared to what we have today and how much it was to add Brotli and such, but it's certainly a trade-off. One of the ways that zstd improves compression over gzip and others is by using more memory. So gzip, I think, has by default like a 32 kilobyte buffer that it works with, and with the higher zstd levels, that buffer can grow into the megabytes. And I believe that the compression level also decides the decompression memory required. I may be wrong on that. So there is definitely a memory trade-off here. Basically, you're getting CPU speed increases and compression ratio increases for more memory usage. And then from a CDN perspective, of which Akamai is one, there is obviously some downside to potentially having to store zstd content. If you think about how CDNs may store various content in their caches, it's often keyed based on the content encoding because different browsers speak different content encodings, accept encodings. And so, for example, today browsers probably, if they are serving up or if CDNs are serving up Brotli content, they probably have potentially a gzipped version and a Brotli version sitting alongside each other. And this would add another cache key essentially with zstd. So you would get more cache entries, more cache churn, lower hit rate in some cases, depending on the usage and how widespread adoption would be. But it's definitely something a CDN would consider before implementing this. And there's always the just kind of challenge of origins are often speaking gzip still today and relying on the CDN to translate that to Brotli or something else. And so if origins are still speaking one compression scheme and the CDN wants to give a better one to the end user, there's always like a decompression, recompression that needs to happen until origins also speak the same compression. So it's not, it's not just a 100% win. I think there's still a lot of research and experimentation that both browsers and CDNs and others would want to do here. Last thing I'm going to touch on really quickly is dictionaries. So Brotli ships today, my understanding, with a 120 kilobytes standard dictionary for the web. I've read some discussions that may be a little bit biased towards older web content, as some of the seed of the dictionary is particular language focused and doesn't necessarily have all languages in it as as the seed data. I think zstd would probably need to ship with something similar for the web, especially for smaller files, smaller content. And so there's always the question of delivery of that. If we could do it like Brotli, where it would be another 120 plus kilobyte payload that would ship with it. But there's also the potential zstd supports other custom dictionaries. You could consider a world where the origin has a custom dictionary based on the content that it knows it's going to serve, and that would potentially bootstrap some of the compression that could happen per origin. That's a very complex topic, and I'm not super well versed on it. I know there are privacy, security, and other performance trade-offs with having like a port origin shared dictionary, but you could consider something like an origin policy, or even building up a dictionary over time on a persistent HTTP connection as a way of making zstandard more efficient with smaller content. So that's all I had from a presentation point of view. Would love to just hear feedback from either the browser vendors on any interest in experimenting or not, and or other CDNs or other services that have looked into zstandard at all. And Yov, if you want to stop recording too.